In our previous video about EMC, we were talking about how to reduce these conducted emissions. And in this video, we are going to learn how you can measure these conducted emissions directly in your lab. And it can be super useful because this is one of the tests when your product needs to go through EMC and EMI testing. Your product has to pass this test. And if you know how to do it in your lab, it can save you some time and also quite a lot of money. So in this video, we are going to talk about the setup, what you will need to make these measurements. We will talk about all the devices which you may need, also how to connect everything together. We are going to talk about what is behind of these measurements, so you understand what we are doing and why we are doing it. And also we will talk about the things what you may need to be careful. You know, when you set up something, you need to be careful to be sure that you are measuring what you really would like to measure. Because I'm not an expert for EMC, I had a call with Arturo. I recorded this call and that's what you will see in this video. And that's everything what I wanted to say for introduction. So basically we are ready to play my call with Arturo. I really hope you will find it interesting and I really hope you will learn something new. Arturo is going to start our call with talking about spectrum analyzer and its settings. Here is my call with Arturo.
This is the screen of the spectrum analyzer. You can see that now I am using the full span. In spectrum analyzers, you can specify the start and the stop frequency, or sometimes the center frequency, and what we call the span is the window you want to analyze. No? Now I am going up to 1 gigahertz. So for example, if I switch off my device, you can see that the low frequency noise disappear because we are going to analyze a conducted emission problem. In this case, so I will be switching the spectrum window to something like 30 megahertz. So in a spectrum analyzer, one of the first things you do is to specify the frequency range with a start frequency. For example, 150 kilohertz. Usually in conducted emissions, we start in 9 kilohertz or 150 kilohertz, depending of the product. And the stop frequency, that is 30 megahertz in this case. You can do this manually in the keys of the instrument, or you can do connecting to the instrument through LAN or any other connection, USB or something like that. So what you see now is the noise level. So this is very important to check how is the noise level before switching on your device.
So you can our device is switched off right now.
Yes, the device is off, and this is something that is very important to do before doing measurements, so you can detect any kind of noise that is from your laboratory or any other device that is close to your setup. No? And you can see that now I am not able to measure signals below this limit, okay, below this yellow limit. No? And in a spectrum analyzer, you usually have options that are called bandwidth, and you can selection the resolution bandwidth or the video bandwidth. They are different. The resolution bandwidth is something related with how the signal is processed in the chain of the input port, and the video bandwidth is a filter that is used at the end of the chain to change how you see the signals in the screen. No? So, for example, now the resolution bandwidth is 300 kilohertz.
So this is basically how it is sampled?
Yes, not sampled, but depending on the instrument, it is analogic or digital. This is related with how how is the width of the filter you are using in the output of the mixers in the super heterodyne structure. You are using an analog system. So if you use a big resolution bandwidth, the sweep in the frequency range is very fast, but you will not be able to identify what frequencies are below this mountain. If you want to identify,
so it's not so precise.
Exactly. Okay. So, for example, I am not sure if we can do. If you are interested, we can introduce a signal from the signal generator to the spectrum analyzers to see the difference. But I think with the noise, we will be able to see. No, I will do it with the noise from the instrument. Something that is important when you are measuring conducted emissions is to know how is the start, how is the stop, and how is the resolution bandwidth that is mandatory for your measurements.
So you will find this information in the specification of the test?
Exactly. In the specification of the test for your product, medical, automotive, or home appliance, something like that, you will find how you need to configure your receiver to make a good measurement.
Okay.
So a typical values, for example, for the resolution bandwidth are 200 hertz, 9 kilohertz, and things like that, no? But this is important for going to a laboratory or to do a formal certification. But when you are doing debugging, you can use similar values, not exactly the same, because you will see the noise and you will be able to work to reduce the level. So something like that. So now I will be using 300 kilohertz.
Okay.
No? Now I switch on my device. So you can see when I switch on my device, I have a lot of noise that increase, no? It's a noise that is going from the low frequencies to the high frequencies. Sometimes this is not in this way. Sometimes you have only noise in the low frequency, or you have noise in the high frequency. It depends of the product. And something that is very important is that if the noise increase close to 30 megahertz, this is dangerous for radiated emissions, because radiated emissions are measured from 30 megahertz to, I don't know, 1 gigahertz, 6 gigahertz. So what happens if your noise is increasing in conducted emissions when you go close to 30 megahertz? That means that in 40, 50, 60 megahertz, you will have noise. If the conducted emission noise is going down, typically this is good for radiated emissions in the frequencies from 30 megahertz to, I don't know, 80, 90 megahertz.
So when we say radiated emission, it means when we go to the lab and they will use the antennas and measure basically the environment around your device.
Exactly. With this test, you are trying to control how is the noise you are injecting conducted through the mains cable or through the power supply cable. In radiated emission, you are detecting how is the emissions that are going from your device to the environment as radiated through the air.
Okay, so what do we see on the scope or on this analyzer? Sorry.
Okay, so what I see here basically is that from 150 kilohertz to 30 megahertz, I have this noise level in my setup.
And is it bad? Is it good?
It's bad. It's bad because it's a lot of noise. But obviously, to know if this is bad or not, really, what we need to plot at the same time is the limits of the regulations. I can show you something that is similar. It's the same noise, but it's not in linear scale, the horizontal plot. Let me show you something like this. We will go later to this again. So let's go here. No. So if you are looking at how is the emission from your product, you compare with the limits from your regulations.
Can you show these limits also in the spectrum analyzer?
Yes, you can do this. You go to the the software program directly the spectrum analyzer or the EMI receiver, but you have something here that is called lines. You see, with lines, you go here and you can specify typically two limits, the upper limit and the lower limit. Why? Because basically you can do this for any kind of work with a spectrum analyzer, but using this for conducted emissions, you can use the upper limit for the quasi-peak detector and the lower limit for the average detector. What is this? In conducted emissions, you can put the detector of the spectrum analyzer, trying to measure something like, you can think about the peak of the noise. That is important. But additionally, you have to control how is the average of the signal. No, you can have, for example, a noise that is very big in peak, but is not repetitive. Okay, and some noise that is not very big in peak, but is repetitive. So with this kind of detectors, the regulations try to control both situations. No, and then you plot the limit in the screen of the oscilloscope. But usually in this instrument, for example, you go to upper limit and you load from a file. So you create a file that is very easy, is frequency value, 2, 3, 4 points. And with the 2, 3, or 4 points, you see a line that is the limits for your product. No?
Do you have this kind of file also?
No, I have not this kind of file here, this instrument, but I have this. This is another software to control the same instrument, and you can plot here. No, so what you usually do is something like this. You go here, and I will explain this later, but if I want to select the test, for example, let me see here, limit lines, no? So for example, here in limit lines, you have for some specific normative, how is the limit line that you need to apply. So you import this file and you configure the instrument with this file. This is what you have seen here, no? This is the same instrument, but with the test that was prepared before this recording.
Okay. So why we are not using this this software with the analyzer?
Well, you can start. We are starting from the easier way.
Okay. So this is like the simplest.
Yes.
Thing.
It's not. Yes, exactly. For example, if you are in the laboratory, you have the instrument, you don't need the computer. You can do this all manually, no? And you can import the file with a USB memory.
I understand. So basically, this what we see is some kind of simple spectrum analyzer, and then you have to do everything some kind of manually. But if you have something a little bit more expensive, then you will get this other special software which can make it much easier to do this kind of measurements.
Not really. What you have seen, this is the screen of the instrument, and this is the screen of the same instrument. So the only difference is if you are using this software or manually or the other software, but the instrument is not necessary to have a more expensive instrument. But if you are in your company and you are doing repetitive measurements, or you want to have a more automatic setup, then you can go to this software, and then you can configure your measurements in a more professional way or in a more effective way to save time.
So I understand now. So the other screen is basically like if you would be doing this measurement exactly on the device. That's what you would be doing. Okay.
Exactly. But what happened? I am using the software only because with the camera going to the screen, the picture is not so good like looking at directly to the screen in the PC.
I understand now. Okay. So why this picture is a little bit different from what we see in the other software? Because in the other software there are a lot of peaks, and this is kind of not so noisy.
There are two different important things. One is that in the previous plot, the frequency axis is logarithmic. And this frequency axis is linear. But something that is very important is the resolution bandwidth. Look at this. The resolution bandwidth now is around 300 kilohertz. So you can see that the emissions take this kind of mountain shape. No, this is related with the resolution bandwidth width. If I reduce the resolution bandwidth, I don't know, for example, to 10 kilohertz, look at this. The signal change is the same peak. You can see that the peak of the signal is exactly the same, but because I have reduced the resolution bandwidth, I am able to identify what is below this filter. No, at the same time, the noise level is reduced. Let me switch off the product. I switch off the product. So this is the noise level. No, if I increase from 10 kilohertz to 300 kilohertz, the resolution bandwidth, you can see that the noise level increase. So the idea is that if you want to measure very small signals, it's better to use a small resolution bandwidth. But look at the sweeping time. I hope you will be able to appreciate this in the video. No, now you see how is the refresh of the screen, but look at this, what happens if I use 10 kilohertz. The system goes very slow.
Okay.
It's slower, no? So when you want to analyze a very big frequency range with a very small resolution bandwidth, it's like when you are, it's not the same, but like in a spice, sorry, you are trying to simulate a very long time with a very small step calculation time.
Yeah,
no?
I understand.
Something like this. So the important thing is to have a good setup that you understand, because the idea is to replicate or to be close to the situation in the laboratory for doing debugging or something like that.
Can we change the scale to logarithmic?
No, I think I cannot do this in this instrument. I think it's linear only. Sorry. With the other instrument, I think with the other software, I think I can do this, but not here, because usually this is in the frequency menu, and you can see that I can select the center, the start frequency, the stop frequency, and the frequency mode, but no, I cannot change the scale, okay? But because you can import the file to your computer, you can manipulate later, no? What you can see here is something that is very common in EMI, is that the noise is periodic. So this is a very important clue to identify what is the origin of the problem, because you go from peak to peak, and you can find that the difference of frequencies, I don't know, 200 kilohertz, and you say
it's always the same.
Yes, it's always the same. So that is because it's linear. You see that this axis is linear, so the distance from peak to peak is, I don't know, 200 kilohertz. And
so this means it's all from one source?
Yes, this is typical, no? From digital circuits, from switching mode power supplies, from someone that is switching at a constant frequency, no? This is one possibility. The other possibility is that you have a noise that is not repetitive, no? This is what is really complicated, because when the noise is repetitive, you can identify someone that is switching at that frequency or is oscillating or something like that, no? So typically, the origin of a problem that is not periodic is something like this. Consider, for example, that we have this one. Let me go here. So I have something like this. This is the limit of my regulations, and I get something like this. Yep. Something like this. And this frequency is not related with any frequency you are switching or something like that. Typically, we have two possibilities. The one is that you have resonance, typically a parasitic resonance. So, for example, in power electronics, it's very common to have this. Okay, so you have ringing. So why you have ringing? Because you have inductance, you have capacitance, but you don't have resistance. There are no losses. So this is an underdamped situation. So the solution for this problem is typically to introduce some kind of losses with resistors, with ferrites. So you try to kill the resonance, and then the emissions goes down because you are killing this resonance. And the second possibility you can evaluate is to have a parasitic oscillation. You are creating an oscillator. You don't want to do this, but you are creating this. So you have a system and you have some kind of feedback between the input and the output. This is a typical problem from layout. No, you put the traces or the cables in your system one close to the other, from the input to the output, and you create a parasitic oscillation at 356 megahertz. No, this frequency is not related with your system, but is something that is parasitic.
And it's super hard to find actually where it is happening.
No, it's hard, but you have tools like, for example, near-field probes. With near-field probes, you can go around the circuit and you can identify, the noise is coming from the DC-DC converter, no? And then you can try to analyze how is the schematic, how is the layout, and you can try to do something in the prototype to confirm if this problem is or not. For example, if this is a trace, you can try to cut here with a cutter, and you can put a line far from the original layout. No, if the oscillation stop, that is clearly a situation of this parasitic feedback. No, not easy, but you have possibilities to do things with this.
And if you have these regular peaks, does it mean that the first one is the frequency which is causing all of the others? Or it can be also somewhere in the middle, or it will be the highest one, or which one will be the original one?
Usually is the first one. The first one is the first harmonic, and then you have the others, the second, the third, the different harmonics of the system.
And harmonics would be always like a multiplier of the first one, or?
Yes, second or odd or even harmonics. No?
So it would be like, for example, 100 kilohertz, then 200, and then 300 or 400?
300, yes. 1, 2, 3, 4, 5.
Okay.
With n frequency, so where n is an integer.
Okay.
Okay. So this is really, no. Sometimes you have a mix, no. So you have frequencies noise that is created because this continuous and periodic oscillation, but you can introduce additionally parasitic oscillations or ringings that create this problem. For example, let's switch here again so you will understand very well this idea. No? If I have something like this in my circuit, what I will be expecting is something like this, plop, 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 plop. Usually the amplitudes, you go very far in frequency, you will see that the amplitudes are going down, no? But this is related, this is the first, this is the second, this is the third. You can see that in Fourier theory, the even harmonics don't happen in a square wave signal, but this is only if the square wave is ideal. And that means rise and fall times are 0, and duty cycle is 50%. This is in our signals, you don't have usually this, so you find the second, the fourth, the sixth harmonic, no? But if you have something like this in your circuit, so that, for example, this is very common in electronics, what you can find is something like this. You can find the different harmonics, and at some specific frequency, you can find the peak. No?
Because of the other frequencies which are in the ringing.
Exactly. The ringing in the signal is introducing energy at some specific frequencies. If the limit of your regulations is in this way, you will be failing. Not because the harmonics, is because you have ringing, no? So both problems are one close to the other.
Okay, so we can go back to our spectrum analyzer. Huh?
Let's go here. Yeah, this one.
So from this, it is actually not like super easy to find out the exact limits. So it would be better if we move to the other software so people can see how this system is failing, or what can we do in this other.
We can try to let me see if I can import some limit. Let's go here to lines.
Okay.
Let me import the file from file. For example, here I have some.
Oh, you have some. Okay, perfect.
Yes. Let's try to do this. You can see here that I am opening a lot of limit lines. So you can have in your computer the typical levels you are using in your application. No, for example, let's try. I don't know. For example,
usually people may be interested in automotive or the lowest one, which.
Yeah, you see. Okay.
Okay.
So I am importing a limit. This one. This is not for a DC-DC converter like I am using now. It's only to show you the idea, no? So you can see in red color is the limit line from this.
Says
so,
pass.
For example, this product, if we want to pass this test, this regulation is perfect. Why is perfect? Because we are below the limit at least 6 dBs, something like that. Because if you are over the limit, you fail. But if you are below the limit, I don't know, 1 dB, 2 dBs, this is not a good situation because from model to model, from unit to unit, from laboratory to laboratory. You can have some kind of differences, no? For example, from one laboratory to other laboratory in the same country, you can have differences, I don't know, plus minus 6 dBs, no? So perhaps in your laboratory you are failing, and in the external laboratory you are passing, or the opposite, no? So I usually recommend to be below 10 dBs, no? Or 6 to 10 dBs. Obviously, to be a lot of to use a lot of margin is usually more expensive in time and perhaps in cost. You need to analyze, to introduce another component in the filter or something like that. But it depends of the company.
10 dBs from the limit, yeah?
From the limit, yes. 10, I like 10 dBs, but usually if you are 6 dBs below the limit, it's a good situation. Remember that if you are working in power, this is voltage, but you will be working in power, 6 dBs is, 3 dBs is half. So 3 dBs and 3 dBs is divided by 4, no? So it's a good reduction, it's a good margin, no? And I have been working with companies that they have the internal limits of the company. So the internal limits of the company are not where the official limits are. So they are, I don't know, 10 dBs, 20 dBs below the official limit, to be sure that the product is perfect. This is typical from very big companies with good EMC laboratories or people. If not, for small size or medium sized companies, this is very difficult.
Okay, so what else we can do here in this spectrum analyzer?
Basically, this is something that is enough to understand the problem. So you need to understand that what we are doing is sending the signal we are injecting in the power supply to the spectrum analyzer or to the EMI receiver. We configure the spectrum analyzer following the regulation criteria, and we can plot some kind of limit to see if we are below or over the limits. No.
So shall we show now the setup, what we are using, what we are measuring?
Yes. Let me switch to the camera. Here is the setup. Okay. You can see well?
Yes, I can see it.
Okay. So in the setup, I have several elements. The first element is the spectrum analyzer that is here. It's an FPC 1500 instrument from Roland Schwartz. Later, I will show you the scope, the oscilloscope, because the oscilloscope can be very useful too for EMI debugging. And you can see the general setup for our application here. No, I have prepared a DC-DC converter where the load is a small fan, 12 volts fan. No, so I need to power the DC-DC converter from a power supply that is more than 14 volts that are coming from this cable. Okay. So from this cable, I go to my power supply. It's a power supply. Let me try to move the camera so you can see my power supply. Power supply is here. Okay. And I am going with my power supply to the setup using 2 wires, black and red. You can see that?
Yes, I can see that.
I am going to this block. What is this?
So black and red, it means it's the minus and plus.
Exactly.
And minus is isolated from ground and from everything else.
Exactly. You can see here that I have several metal plates in the regulation documents. You have the explanation of how this setup must be done. No, usually regulations documents must be paid. So it's a document that you need to buy. No, but for example, if you go, let me go here to this is, for example, if you go to Google, you Google, for example, DC conducted emissions measurement CSPR 25. I don't know, you are interested in this standard, and you go here and you will find some documents where, for example, you can find some replica of what you will find in the official regulation. No? So for example, here you can find how, following this CSPR 25, you can find the idea here. No, so is the power supply must be out of the setup. This is a metal plate. this is your device under test. This is the artificial networks. This is the line impedance stabilization network. We will explain later. That must be connected to the metal plate. If your device needs some kind of load, I don't know, motor or something like that is out of the setup. And then if you go to the vertical, you can find some explanation, like for example, that the device under test must be over the metal plate with some dielectric material with some specific thickness.
It's like 50 millimeters. Yeah, I see.
Yes.
Distances are in millimeters.
Exactly. Okay. So, for example, in my setup, I am using this dielectric material to isolate. But, for example, you can be interested in using 5 centimeters or 3 centimeters, and you can use. Later, we can do the change so you can see the difference.
Okay.
This is the general idea. For example, if we go to the previous screen and we remember, for example, that my emissions are, I don't know, around minus 70, no? The value of minus 70, what we can save, no? In this oscilloscope, in this spectrum analyzer, we can go to trace, we can go to save, for example, view. And now we can go to the second trace that is in green color.
Okay.
Okay. And then we can move the distance. So let's go here. Let me see here. So you can see the difference. Okay. So what I am going to do is to increase the distance between my device and the table. Okay, the green is the one that is being refreshed.
The new one, now. Okay, yeah, I see.
Is with the distance increased.
So
and the yellow is when the thickness of the dielectric material is smaller.
Okay.
Okay, this is related, for example, with the common mode.
So when we pull up the unit away from the ground, the emission what we measure is lower.
Exactly. Let me remove this one and let's go to trace number 1 and let me clear right. You can see let me select the resolution bandwidth, for example, instead of 10 kilohertz, let's go to 50 kilohertz. So the sweep is faster. Okay, it's sweeping, you can see. And then let's put here and you can see the difference. So now, increase, and if I go up, decrease. So
I remember you mentioned that you don't really want to have your hand close to the measurement because it can influence.
Exactly. Well, I can repeat the experiment. This is very important. If you touch the device, you are working like a part of the circuit for the common mode, so you can affect measurements. But let me repeat the test without touching, no? So this is the situation when the device is very close to the metal plate. This is the situation with the distance, and I remove my hand. And you can see the difference, no? When the product is closer, you have more injection to the metal plates. The metal plates are connected to the heart system. And this heart system is not connected to the negative rail, no? So this is a DC power supply. So this is plus 16 volts, and this is ground, 0 volts. But in a mains application, this is line, this is neutral, and neutral is non-connected to earth. This is exactly the same.
Okay, so I would like to mention, or I would like to add that some power supplies, they actually have the third output, which is basically the chassis or ground of the instrument. So you have like 3 outputs from the power supply, the 0, plus, and then the ground. And sometimes you would like to connect the ground together with the 0, and sometimes not. So in this case, it is not connected.
Not connected. It's floating. The ground terminal is floating related with the heart system or the metal plate reference. Okay. Okay, so later you see this. What is this? Really, this is not necessary, but I usually work with this kind of filters because I want to avoid that noise that is coming from the power supply or from my laboratory, or that is picked up by the cables. You can see, for example, that in my cable, I have a ferrite in common mode. I have more ferrites here. You can see, okay, I have more ferrites in the cable. This is because if you connect directly in a room or in a laboratory that is not shielded with good filters in the power supply system, you will be able to see noise that is not coming from your device under test. So something that I usually work with is this kind of filters. I have prepared the reference for this filter. So in case you are interested.
Yeah, okay. I would like to know what kind of filter.
Yes, this is the filter, but any filter that you can find in the market for EMC, no? These kind of filters are filters that are for the 250 volts or 120 volts in the USA powering applications where this is line and this is neutral, and they are designed to pass 50 or 60 hertz. But because this is a low pass filter, DC levels go from one side to the other without attenuation. No, obviously you can change this by I don't know, a DC filter, no problems. Okay, but I am using this kind of filter with success. So
because this is kind of more universal, you can use it in all the kind of different measurements.
It's very easy to find these filters from many vendors, and from you can buy these from many of the typical distributors of electronic circuits. No?
Okay.
This is the idea. So let's go to the screen again. Let me here. So this is, remember, to avoid the noise going to the setup. And then I have to line impedance stabilization network. What is a line impedance stabilization network? It's an element that is very important because with these elements you have three different functions.
Okay.
Let me try to explain the idea with the drawing. So this is basically, this is the setup. This is the setup I have in any kind of, I am using DC levels, but it's the same, no, positive, negative, and hertz. No? So if this is your product, the noise you are injecting in the power supply system is dependent of the impedance you see in this network. So it's impossible to measure in Spain, in Germany, in London, in the UK, in Italy, in different laboratories, and to compare the noise you are injecting with the same limits, because the noise you are injecting is depending of this frequency. So that is because we use this black box, this metal box that is called line impedance stabilization network. The line impedance stabilization network is a way to see, to control how is the impedance you are offering to your product in common mode and in differential mode in some kind of a standard way.
So basically, we use it because the noise which is coming out from this device, it can be, for example, very weak, and if the impedance is very low, then this noise would kind of disappear.
Exactly.
And if you have higher impedance on your power supply, which is powering this device, then the noise would suddenly will be visible. If you have lower, it would disappear. So basically, you need some kind of standard impedance, which then which is used as some kind of I don't know how to explain. It's the reference, basically.
Exactly. The idea is something like this. If this is your device under test and you are injecting noise, if for example, the differential mode noise is the noise that goes from the positive and is returning through the negative, line and neutral. So what happens if the impedance you have in your mains network is very small? If this impedance is very small and you think in current, it depends if you are thinking in current or voltage, it happens similar to what you say. The noise in current that you will be injecting will be very high. But what happens if the impedance in another system is very big? The noise looks like it's smaller because the impedance is bigger. So it's impossible to compare with a limit if this impedance is related with the impedance in some specific.
So, I would say when impedance is higher, then also noise.
It depends of what you are considering.
Maybe it depends on.
Yeah, if you are measuring
if it's current or voltage. Yeah, okay, I understand.
No? If you think in your way, the idea is that instead of thinking in current, think in voltage, no?
Yes.
The voltage you are creating here with a big impedance, loading impedance will be very big, but the current will be very small, no?
Okay.
But the thinking is exactly the same. No? So this is the first thing to do with a line impedance stabilization network. The second important, this is the first. What is the second important part of the line impedance stabilization network? You can see here, this one and this one. So the idea is that while you are doing the test, your noise is not able to arrive to the line, to the mains network or to the power supply network. And additionally, the noise that you have in this power supply system is attenuated. So the idea is to measure the noise you are creating, not the noise that is coming from outside. It's some kind of the reason, because I am using an external filter. I am using an external filter to minimize more the noise that is coming into my setup. No? So, and the third, this is the second function, and the third function is this one. You have a connector where it's very easy to connect a coax cable to go to the EMI receiver.
So it's the measurement, basically.
Basically, you don't need to open the wires. You don't need to consider where you need to put a voltage probe or a current probe, in what point. No, directly in the box, you have this connector that is prepared to go to a 50 ohms load to show you a voltage. And this voltage is the voltage that officially must be compared with the limits.
So now the question is basically what is inside of these black boxes? So we mentioned we need it for three things. We need it for the impedance. We need to have it there to connect our spectrum analyzer, and it's also doing some kind of filtering. But we would like to know what exactly is inside of these black boxes.
Okay, so in general, what you can find here is a way to control how is the impedance you see in your setup system. So you need to offer some known impedance between your for your system in common mode and in differential mode noises. So consider, for example, that this is your device under test. If you consider that this is the line, or for example, the positive terminal of your product, and this is the neutral, or for example, the negative terminal, what you know is that this is the wire, and this is the power supply or line. This is the neutral or the negative, and you have this. And additionally, you have here the hearth or the chassis of your product. It depends of the product, no? So what happened? The noise you are injecting in differential mode, the noise you are returning in differential mode through the negative is related with how much is the impedance you have here. If the impedance is different, the noise you will be injecting is different. So we need some kind of circuit to show to your product a known impedance, so we can compare the result of the measurement with the limits of regulations in any country, in any laboratory, in any condition. Okay, so the idea is, how is the impedance we see in a network? If you measure how much is the impedance in a typical power supply system as a function of frequency, you will find that it's something like this. Is doing something like this. Consider you are measuring experimentally, and something like this. This is the envelope of the impedance you can measure in a real application in the world. No, this is something like, I don't know, perhaps 10 ohms, and this is something like the maximum is around 500 ohms. And what happened? The impedances do something like this, and this value is around 50 ohms. So if you take this plot like some kind of reference that can represent between the maximums and the minimums, the typical behavior of a power supply system, look at this, from around 100 kilohertz, what I am looking is a constant value. But in the first frequency range, what I observed is some kind of inductive increase. No? So this is what we have inside of the black box or the metal box or the line impedance stabilization network. The first things to consider is how I can make independent the noise I am injecting. Let me draw in blue color the common mode. The common mode is in this path, is returning in this path, and is returning in the hard system. This is 2 times the common mode. No? So, for example, how can I make independent this noise from the impedance in the network?
I have one question.
Yes. Let me know. Yes.
Some people may ask, what if your product doesn't have any chassis? How this common noise is going to be picked up with the board? And I guess it's through the capacitance from the metal plate and to your circuit, for example. That's what is happening, because it's capacitor, then the noise is coming, and that's why we place it closer. More noise can go because it's shorter. Exactly. Okay.
That is the idea. This is typical, for example, from products in mains network that are called class 2 circuits with double insulation. They don't have hertz connection. Okay, and many other applications.
But in a real application, this noise theoretically will be coming out from your board anyway, because everything will be kind of ground.
Yeah.
Okay, I understand.
In radio frequency, there is no the concept of disconnection. In radio frequency, always you have things connected through this kind of parasitic capacitances, no? So what happens if you put a capacitor here or a capacitor here? With these capacitors, you are creating a short circuit between lines. So there is no effect of the variations in the impedances on the left from what your device is looking at. So this is some kind of short circuit.
It is some kind of short circuit. It means, from your device, all the noise will be going through these capacitors, basically.
Exactly.
And it doesn't go more to the power supply, which is...
Exactly.
And we do it this way because then we would like to somehow measure this noise. Okay, I understand.
If I put the capacitors in this position and they work like a short circuit, it's true that the noise will go through these capacitors. But when I finish the total circuit, the noise will not go through this capacitor.
Okay.
You will see.
So let's continue.
Okay. So the idea is that if you put these capacitors, the idea is that the impedance you see versus frequency, thanks to this capacitor, would be 0. This is unuseful, no? It's a short circuit. So this is not what I want, really, okay? So the idea is, consider this is a capacitor that is a short circuit. Now I introduce an inductor. Look at this, I am introducing 2 inductors. And this inductor creates this effect. It's increasing. And the increase of the value would be to the infinite. I don't want to go to the infinite, no? I want to have less. With a resistor, with a resistor, I will control the maximum impedance for this inductor. But consider that it's increasing, no? And then what we put here, so the impedance that is important is the impedance we see from this point and from this point to the left. So now I put another capacitor here and another capacitor here. Why these capacitors? This capacitor is some kind of way to sample the noise. So the noise that is differential mode goes in this direction and find a low impedance path, and the noise from the differential mode will be returning through this capacitor. Now I put here a resistor. This resistor is a 50 ohms resistor that is not really in this position. This resistor is this.
is the long coax cable terminated in the 50 ohms of your instrument.
Remember, this is the connector. So if this connector is this point, the 50 ohms resistor is the 50 ohms transmission line terminated in the 50 ohms of your instrument.
Okay,
so
that's basically the connector, or exactly. In the box, in the black box, there will be basically the connector.
Exactly. You will find the connector that is the output of the line impedance stabilization network. But what happens if you have, if you want to measure the noise in the other line?
You have exactly the same. You will have this capacitor and you will have a resistor, okay?
Because we only have one instrument, one spectrum analyzer, while if you are measuring this line, the noise, for example, in the positive line, you connect the connector to the instrument, and the other is terminated. You can see here that I have a 50 ohms termination. So in this way, the system is symmetrical.
And this is how you basically need to measure it.
Exactly.
And then what is this? This is another resistor that is inside of the black box, something like that.
I am not explaining that this is the circuit that is specifically inside of these black boxes.
Okay, it's just generic idea.
This is a very simple schematic for a typical line impedance stabilization network. In a real impedance stabilization network, you can find more inductors in series, several capacitors, and additional components to model the line. But basically, this is the idea, and if you work with this, it can work very well. These 1K resistors are for being able to disconnect the charge in the capacitors. They are for discharging the capacitor when you disconnect.
But you can see that the noise will not go through the 1K resistor. They will take this path, they will take this path, and they will take this path. So let me give you a question. How is the impedance we see in differential mode?
100 ohms.
100 ohms. Because it's 50 ohms in series with 50 ohms. This is not really true because the impedance is not constant, no? It's not 50 ohms. At this point, it starts to decrease. But for frequencies higher than tens of hundreds of kilohertz, you can consider that the impedance, these kind of black boxes offered to your product, is something like 100 ohms. This can be very useful to simulate in a SPICE or something like that, a value easy to
filters or something.
Okay.
And what happened with the common mode? Look at this. The common mode is taking this path, is going to this resistor, is taking this path, and is returning in this direction, and the other is taking this path, and this path. This is the idea. But the voltages you will be measuring, remember, are this voltage. Let's call this V1, and this voltage V2.
And both voltages must be below the limit. You need to measure the voltage in the positive, the voltage in the negative, to compare with the limits, and both voltages must be below the regulation, or the voltage in line and the voltage in neutral.
So basically, if you would like to, for example, simulate this, then does it mean the common mode impedance is 25 ohms?
Exactly.
Okay.
Good point. The common mode impedance is more or less 25 ohms.
Really, many people, when try to simulate this, for example, with LT SPICE or something like that, they model the full line impedance stabilization network because it's a circuit that is very easy to simulate. No, if you want a perfect representation of the impedance of the LISN. If not, you can do this approach. No, differential mode 100 ohms, common mode to 25 ohms. It's a general rule. And these voltages is what you get in the connector 1, V1, and in the connector 2, V2. When you want to measure V2, you change this load impedance to this connector and you move this cable to the other connector.
Are
You
they
see?
going to be different? I would expect they would be like similar.
Usually they are similar, but sometimes could be different. I don't know
Okay.
because okay, but you need to check both of them. So what is inside of the typical commercial line impedance stabilization network? You have different possibilities. For example, this can be in a, let me take this drawing in yellow color. This can be in a box. So if you want to do measurements, you need to buy 2 of these line impedance stabilization network, or you need to measure in one and to change the cables to the other line when you want to measure the other line. Other line impedance stabilization networks introduce several switches. So you can, with a switch in front panel, you can configure, I want to measure line, I want to measure neutral. And the cables route the signals to the appropriate connectors.
So do you have some examples of these devices?
I don't know exactly now, but you have in the market this kind of line impedance stabilization networks. Okay. So the idea, in this way, the line impedance stabilization network usually is cheaper because you only need one circuit. And only, in my opinion, the problem is that this routing of the different points of the circuit to the switch must be very well done to avoid, how to say, non-equilibrated paths for the common mode, no? Because with this kind of switching activities, you can create a non-symmetrical behavior for the common mode. But there is good line impedance stabilization networks working in the market with this. And finally, you will find in the market line impedance stabilization networks where you have 2 connectors, and then you connect in this in both of them when you want. No, without, it's like if we introduce in a box the 2 boxes you see here in black color, we introduce in the same box with 2 connectors. So this is the idea.
Okay, so what model exactly you are using here?
This one is the tech box. It's a tech box line impedance stabilization network. Let me try to show you with the camera. Let me go here and here. Okay, let's go here this way, here, and then you can see. Okay, so this is a tech box line impedance stabilization network that is for DC, maximum 60 volts and maximum current 10 amps. Okay, it's for DC. But for example, if you want to go to, this is typically for low power application at very small circuits. But let me show you a typical line impedance stabilization network like this one, for example. Okay, this is typical for power electronics, no? This is for automotive, or you can find bigger with kilowatts when you want to measure the conducted emissions in systems like, for example, motors or battery chargers or things like that. Remember that you need to specify the line impedance stabilization network must support the 20, 50 amps, 100 amps that are going through the line or through the neutral or through the positive and the negative, no? So this very small box is not able to support this current or perhaps a higher voltage, no? So and this is the idea.
I guess everyone noticed all these metal tapes. So does it mean we need to like very well connect all these boxes to the ground?
Yes, exactly. I am trying to fix all of them, not specifically in this case, because this metal box, this is a metal box, but it's painted. So the problem with the paint is that it's not conductive, no? But when you want, for example, you can see here, I am using tape too, okay, in these points. So this is a way to connect with low impedance the different elements of your setup between them, no?
And the shield of the cable, which is connected to the spectrum analyzer, the shield is connected to the ground again, from the schematic what you draw. So the spectrum analyzer is basically connected to same ground as the ground of the big player.
Exactly.
Okay.
To the hearth system.
Yeah.
Because this connector is connected to the chassis is connected to the hearth, and this hearth and this chassis is connected to the shielded connector of your coax cable.
Okay. There is one more element, what you can see. Yeah.
This one.
Yeah.
This is the transient protector. Okay. So this is the idea. Something like this.
You can see here, no? So you know what is your product. You put here your device under test on a metal ground plane. The power supply is outside. You can use one or two line impedance stabilization networks. If you are measuring in one of them, the other is terminated with 50 ohms. So the coax cable that goes to your receiver has this additional element. This additional element is a transient protector. It's a peak limiter. So this is especially important in power electronics, because if you are measuring the noise that is created in some kind of system, you can create transients that can create a lot of problems in the spectrum analyzer or in the EMI receiver. So this kind of transient protector usually have some kind of attenuation. I don't know, 3 dBs, for example, has a broadband behavior to cover all the frequency range of interest, and usually have some kind of diodes limiting the possibility to have peaks negative or positive. They are working clamping this kind of transients. No, this is very important because obviously you are protecting the circuit, the internal circuit of the instrument to be damaged. But if your instrument is destroyed, you will know that the system is not measuring, and this is not a problem more than going to the manufacturer, asking for repair and calibration. But what happens if you don't destroy the circuit and the circuit start to measure in a wrong way? Is damaged, no? Perhaps you will discover that the instrument is damaged, I don't know, 1 month or 3 months later.
So basically you can damage it and it still may look like it's measuring something.
Yeah. This instrument, this is not like the oscilloscope. Oscilloscope usually are more robust instruments, no? But a spectrum analyzer with a very high dynamic range have internal circuits with amplifiers or mixers or circuits that are prepared to work with very small signals. So usually the maximum signal you can apply in the connector is very small, and this kind of protector. No?
So why they don't build in this protection inside of the spectrum analyzer?
You can find some instruments perhaps with some kind of attenuator or protector. Really, I think that these instruments don't have protectors, but you can have some attenuator that you can connect or disconnect if you want. But if any kind of element you introduce in the input port is a limitation for the dynamic range of the instrument. You will not be able to measure very small signal. And this is a problem because when you are measuring very small signals, you don't need this transient protector. No, mm-hmm. So it's better to have this externally. Mm-hmm. Okay. But this is very important to know how is the frequency response of this element, or for example, how is the losses of the cable in the frequency range, because then you need to introduce in the spectrum analyzer or the EMI receiver what we call the correction factors. Okay. The correction factors is that automatically the instrument correct for you how is the real amplitude of the signal you are measuring. No, if not, for example, if this is a 3 dB attenuation, the signal in the screen looks like it's lower than really is, no, because it's being attenuated, no. So it's very important to know this. No?
And I guess it's not so simple. I guess the characteristic may not be like completely flat. It may be different exactly. for different frequencies. Exactly. And you need to somehow place this characteristic inside of your results, or
yes. But usually in the EMI receiver or in the let me see if I can show you here. Let me show you. I don't know exactly in what menu is this. Lines. Let me go to this software that is here. No, you can see here transducer correction. Mm-hmm. So usually this is a file. So for example, you can find here different transducer factors for different elements. Let me see if there is here. This is the transient protector I am using here, or you can use here, is the ESH3. So if we go to the list here, you can see here. No, it's not here, no? But for example, if this
not
transducer,
Z2, there is like only Z5, Z6.
This one, no? I don't know exactly what is the reference from the Rode and Suar name, sorry. But consider, for example, that this transient limiter is this one, no? So you can select it and you can put this transducer in your measurement. It's a frequency dependent response, so it's not a constant 3 dBs or something like that. So you can measure with the spectrum analyzer the frequency response, or the manufacturer gives you the file, no? So it's the same. So automatically you can load this element and the software in the spectrum analyzer make the correction, okay?
So can you load it also directly into the scope?
Yes. I think it's in this way. I am not very familiar with this software, but for example, if I create a new test template here, let me see.
So you will get this software when you buy the spectrum analyzer, correct?
I don't know if this is free. I don't know.
But
usually software is not usually very expensive compared with the instrument. No, I know, for example, that some of the softwares from Rode and Suar are free, and some of the other softwares are paying. And I suppose it depends too from the options you want to apply, no? And from the instrument you are buying. But for example, you can go. This is a line impedance stabilization network. You can open it and you can see. For example, no, another correction factor is from the line impedance stabilization network. So if I want to specify, I can put a fixed correction, or I can according to transducer correction table. This is the file that you have in the computer that is permits to make the correction of the line impedance stabilization network. It's the same if you introduce an amplifier or some specific connector, and this is the same for conducted or radiated emissions. The important thing is to be able to know how is the frequency response of the chain from the antenna or from the point of measurement to the input of your spectrum analyzer or EMI receiver, so you are able to correct as necessary. This is the idea, okay? And this is the point where I have this element, no?
So does it mean that what we see on the spectrum analyzer right now is this already corrected, or it's just?
No, it's not corrected. So think, for example, that I see this, no? So I have in my mind, I know that this is the limit I want to pass. So this is 10 dBs, 10 dBs, 10 dBs. So I can consider that I have here, I don't know, 35 dBs of margin. This is not true, because I have not introduced here the correction factor of my transient limiter. You need to introduce it, no? So you need some time to prepare the setup in the good way to be sure that the measurements are okay. Obviously, if you are coming from the laboratory, from the external laboratory, and you know that you are over the limits in the laboratory, I don't know, 10 dBs. If you go to your company, you can measure without the correction factors. You will see the noise in some specific value, and you can try to work to reduce this value 10 dBs. So you will be working in a good way, because the reduction you obtain is what you want at the end, but you will not be able to be sure how is the peak of the signal compared with the peak of the signal in the external laboratory. This is the idea.
Are there some kind of standard noise generators which you can use as a reference, so you are sure that what you are measuring is really what is generated?
Yes. Typically for many EMC, For many EMC applications, you will find systems that are called typically comp generators. The comp generators are systems that create from some specific frequency multiple signals in some specific frequency range, and they are using some kind of reference source, no? So you can check that your setup is usually working in a good way. Yes.
Okay, so your setup should show exactly the same same results as are specified in this device.
Exactly. These kind of systems are very used by laboratories, official laboratories, and they put the same, they usually share this circuit and they measure in the same laboratories, for example, in the same country, so they can compare the results. So in this way, you can know in my country, for example, how is the typical difference if you are measuring in one laboratory or the other. So you can consider, no, in my country, we have -3, -4 dBs of differences between one laboratory and the other laboratory. No?
Mm-hmm. Are these devices expensive?
Yes, all in radio frequency is expensive. Considering expensive that any connector, any cable, any circuit start to have 3 zeros in the price. So this is the problem with radio frequency, no?
So basically the cables, also even the cables which you use in your setup, they are some kind of standard?
No, they are, the cables I am using are good quality coax cables, but it depends of your work, no? Obviously, if you want to have a very, very good laboratory with controlled results, you will need a good coax cable with a good transmission line with good 50 ohms, with a good shielding, with I don't know, a high coverage in the shield, blah blah blah, with good connectors, with good materials in the connectors, and this will be expensive, no? But in my laboratory, where we are using the laboratory for teaching or for debugging EMI problems, it's not so important to have a very high quality cable.
I guess you still can get good enough results even with like some kind of good cables.
Yes.
You don't need to have like the most expensive ones.
No. It depends obviously it depends of the final application, no?
Okay, so shall we move to this different software, or shall we speak about the oscilloscope?
We can switch to the oscilloscope. This is the software from the oscilloscope. So where is the difference? The idea, I am using an RTM oscilloscope. You have today in the market very high quality scopes where you will find a very high good FFT functions. No.
So if you don't have like spectrum analyzer, you can use oscilloscope and FFT function, correct?
Exactly. It depends on the oscilloscope. No, for this application you need one oscilloscope that is not very old. So you need one of the oscilloscope that today offer good FFTs, very fast option. No, so the idea is very simple. You connect, instead of connecting to the spectrum analyzer, the output of my signal is connected to the oscilloscope. What I have done now is to disconnect the cable from the spectrum analyzer. No, let's go to the camera. What I have done here is disconnecting from here, and I'm going to channel number 1, nothing more. No. So where is the advantage of the EMI debugging? Of the oscilloscope for this application, for EMI debugging? I love to use oscilloscope for debugging because at the same time you see the frequency domain, you can see the time domain. And sometimes in the time domain, you have a lot of clues about the origin of the problems. Remember ringings or things like that. No? So in this idea, this signal can be seen with the FFT. So we can go here, and then we have the FFT of the signal in blue color. Let me increase this one. Okay, let me adjust in this way. So this is the frequency. It's important to go to the menu of the channel number 1 and to check that it's 50 ohms. Mm-hmm. If not, this is very important, because if you look at the screen, the signal is going in this direction through a transmission line that is 50 ohms. in characteristic impedance. And at the end of at the input of the oscilloscope, typically you will have 1 megohm in parallel with 10 picofarads. This is a very high mismatching situation for this frequency range. So you will have a lot of reflection signal, and the signal in the screen is distorted. So to avoid this, we will put here 50 ohms with the menu of the oscilloscope, or if you don't have a 50 ohms oscilloscope like this one, you can put a T, a T. Let me see if I find something like this. Let me show you. Something like this, no? With the camera, you can see here with this. Okay, you can use a T with a 50 ohms termination, like something like this. This is a 50 ohms termination. You put here a cable, and then you connect this here. So you are creating some kind of 50 ohms termination. This is not perfect, but for going up to 30 megahertz can be good for you, no? So this is the same screen you see here with the camera. It's in the software. I am going to this is not a software that is specific for the instrument. It's only IP address. Mm-hmm. So you can access directly to the software that is internal to the instrument. And then you can see how is the spectrum of the signal in this frequency range. No?
But we need to, is the 50 ohm switched on?
Yes, now it's off. So you can see the difference if I switch on, you see? That is different. So you need to try to avoid this error.
Can we do same range as we did in the spectrum analyzer between?
Yes. Start is 150 kilohertz. Sorry, 150 kilohertz.
There is K, no? Yeah.
Yes. Okay. So now I am in 150 kilohertz. Stop is 30 megahertz. This one. This is the same like previously. And let me reduce the vertical scale. It's okay. So this is basically what we get in the time domain and in the frequency domain.
But it's a little bit different when we compare it with the spectrum analyzer.
Probably, I don't know where is let me introduce another element that is not in my second measurement, is the transient protector. I was not using the transient protector.
Yeah.
Let me see if this is part of the problem. No?
Yeah.
Okay, the problem is that this way. Let me see. Now let me move this on top. This one. It's very important when you are doing the FFT in this kind of oscilloscope that the signal in the time domain must not be going over the vertical limits of the screen. If not, the spectrum will be destroyed.
Mm-hmm. So basically the signal has to fit inside of the screen.
Exactly. Okay, so you can see here that...
Oh yeah, now it's similar. Can you change the color because it's not very well visible?
Yes, let me try to do this. And let me change the color.
Okay. Perfect.
Okay, it's perfect now?
Mm-hmm.
You see that it's more...
It is similar.
Yeah. See, you can see here how is the important... What I have done now is to move... in my first measurement, this transient protector was not included, no? So the idea is that now the signal I am measuring is smaller in size, but at the same time, I am introducing the same frequency response, no? So usually when I am working with the oscilloscope, I don't use the transient protector. So, but for the debugging purposes, it's basically the same. But you need to check these kind of things. Or sometimes you can forget to put here the 50 ohms termination, and you do a lot of measurements, and at the end you discover that the termination was not in place. So you need to repeat the test, no? So these kind of things can happen. Okay?
Okay, yeah, perfect.
So this is the idea. You can see that the FFT is very fast. If you do change, changes. For example, if let me show you the camera, and if I move my product close to the circuit, the noise increase, you see? Remember the effect of the common mode. Yeah. If I increase the distance, the noise decrease automatically in real time.
And I think you mentioned the scope also has an advantage because you can do some math.
Yes. This is important if we go again to my previous slide, this one. Let me find the slide I was drawing before. Look at this. Look at this. This is the voltage we are measuring, this one. Let's go here, this one. This one. This voltage.
It's not showing. Okay, it's showing up now.
Okay, and this voltage.
But what happened with this voltage? This voltage is the voltage you are looking at now in my oscilloscope or my spectrum analyzer when I am using, let me go to the camera. This is V1 and this is V2. So we have been looking at the screen in V1 here or V1 here in the scope, no? But what is V1? V1 is 50 ohms times the current in differential mode plus the current in common mode. And what is this? V2. V2 is 50 ohms times the current in common mode minus the current in differential mode. What is important from this picture is that what you see in the screen of the oscilloscope, this picture here, this one, reconnect. This signal is both modes at the same time, common mode and differential mode.
It's combination of different noises.
Exactly. And it's very, very important for the designers of filters to know what kind of mode they want to filter. You know that, for example, for mains application, we have X capacitors that goes from line to neutral, Y capacitors that go from line to earth and from neutral to earth. We have differential mode chokes and we have common mode chokes. So in many situations, in electronic products, what many designers do is, especially in companies where there is no one EMC department or EMI people, is they take the filter that was working in the previous product, in the previous model, and they try to introduce this filter in the new product. And if the system is working, perfect. If not, they try to tune, to change components by trial and error, introducing more capacitors, bigger capacitors, another common mode choke until they arrive to the solution. No? But obviously, if you want to filter common mode or differential mode, you need to do some kind of separation. This is what we can do.
When you would like to filter one mode, you need to use specific components or specific circuit, and to filter the other one, you need to use different circuit.
Exactly. It's very easy to understand. Let me consider that we have the line, earth, and neutral, line, earth, and neutral, line, earth, and neutral, or if you want positive and negative, positive and negative. The idea is similar, no? So if we are injecting differential mode, is the noise that is going in this direction and is returning in neutral, and the common mode in blue color is something that is going through the hair. Let me call this 2 cm, and is returning cm and cm. So in line and neutral, the common mode is going in the same direction. So if you want to filter the differential mode, what usually people do is to connect here a capacitor between line and neutral. This is what we call X capacitor. No, this is related with safety regulations. The differential mode noise is taking this path, and what you want is the noise taking this path and going in this direction. This is what you want to avoid. How you want to avoid the noise going to the
mains network or to the power supply system. Sometimes you can increase the value of the capacitor. You can put higher capacitor, higher, but the problem is with higher capacitor, you have some kind of limits, especially in high voltage application like the mains network, or sometimes a bigger capacitor means that the self-resonant frequency is lower and it will not be working in higher frequencies. So increase the capacitor is not always a solution. So you need to increase the order of the filter. So in this way, you connect something like, for example, another element. This is one inductor. Why on the right and not on the left? Because typically the differential mode impedance in the device under test is smaller than the differential mode impedance in the line impedance stabilization network. Remember that the impedance that is on the left is 100 ohms. And the orientation of a filter, that when you are designing filters with inductors and capacitor, the orientation is very important because you need to put the series component in series with the smaller impedance and the parallel component in parallel with the higher impedance. So in commercial filters, it's typical that the differential mode choke is in the size of the device under test. Obviously, this is not a general rule because you can find products where this is not true and you need to switch to mirror the filter. No? If you want to filter more differential mode, you can introduce another component. You can introduce another inductor or another capacitor. Where you are trying to do something like this. If this is not good for you, you try to do this or you try to do this. No, you start to increase the order of the filter to have more slope in the attenuation band. No, but usually people don't like inductors. So instead of using another inductor on the left to have a T filter, no, they put another capacitor here to obtain a pi filter. Okay, but usually in my experience is that people want to do this. This is they want to do. With one capacitor, they want to solve a problem. Obviously, the idea is to design the circuit correctly to minimize the noise you are injecting. But for common mode, let me consider that you have a lot of noise, and this noise is common mode. And you put this capacitor, the X capacitor, and you think about the path of the common mode noise. Look at this, the common mode noise is going in this direction, and it's going in this direction, and it's returning in this direction. There is no possibility for the common mode to take the path of the X capacitor.
Okay, I understand.
So the common mode noise is something like ignore the X capacitor, no? Or the opposite. If you have an inductor here, the common mode noise, let's go here. Let's remove this one. If I have an inductor here that is an inductor for the differential mode, the common mode noise is exactly the same because it's taking this path and is returning through this line. So you have the common mode current circulating. Obviously, the differential mode inductor introduce impedance in the upper line, but not in the bottom line for the common mode. So for the common mode, you need to introduce another inductor. You need to duplicate one inductor in line, other inductor in neutral, or you need one inductor in Hertz. So the problem is that when you are designing a filter, you need to know from your frequency range, what is common mode, what is differential mode, so you can optimize what kind of components you want to introduce in the filter to minimize the size, the cost, and the weight. This is the main problem with filters. This is the idea. So how can you do this? If you look at this, it's easy to see that V1, now we will be measuring this. So this is V1. So V1 is 50 ohms. That is multiplying the differential mode. Let me remove this one. So you can see that V1 is 50 ohms that multiplies the current in differential mode
plus the current in common mode. And V2 is 50 ohms multiplying the current in common mode minus the current in differential mode. So for example, if you add V1 plus V2, you have 50 ohms, and then this is 2 times ICM.
So if you add the two voltages, you are removing the differential mode. And this is very useful. This is what we call a differential mode rejection network, or if you calculate the difference, is a common mode rejection network. And this is the way to think about this. This is very, very useful. Something like this. Consider that you have this spectrum and you have some limits. So, okay, you know that you need to filter here and you need to filter here, but this is common mode or this is differential mode, you don't know. So then you do this measurement. You introduce a way to add or subtract the output of 2 LISNs or the output of a LISN with 2 LISNs inside, no? It's the same. So if you do this, the first measurement is the normal measurement we have been done. And the second measurement is what happens if you work with a differential mode rejection network. We are adding the 2 outputs. So from these tests, what is your opinion? My opinion is that in this product, all the noise is basically differential mode.
And
so
then you may want to use capacitor, for example.
For example, you can put or capacitance between the lines or a series inductor in one of the lines. In theory, no?
And so this DMRN, again, you can buy this kind of devices. It's going to be, again, some kind of black box.
Exactly. Okay. Here you can find 3 different possibilities to solve the problem analogically. The idea is to use a network that is typically using transformer. If you look in the biography in literature, you look for differential mode and common mode separation, you will find that basically we have 3 different possibilities. One is using 3 resistors. They are 3 resistors, 1% in tolerance, that are combining the signals to add both of them. This is what we call a differential mode rejection network. And the author of this idea was Margie Neff. He's a consultant in the USA. This is what I have inside of this box. You see 2 channels, input channels, and 1 output channel. So the output channel is the common mode. The other possibility is to use this setup that is from the same manufacturer of the LISNs. Is what is inside is a transformer. In the different articles, you will find transformers that can be used for this. And this solution is using a mini circuits splitter. No? You know that in radio frequency, we have power splitters. Let's go to the camera. In the radio frequency, we have power splitters and power combiners. They are used in radio frequency applications. No? So this is the idea. Let's try to make a good zoom. Mini Circuits is a well-known manufacturer of electronic components for radio circuits. So the idea is, instead of using the component for combining or dividing, splitting a radio frequency signal, we add the 2 signals, and in the output we have the combination, so we can use the spectrum analyzer to see the signals. I was preparing the experiment previously to check that it was working. Remember here, the horizontal axis is logarithmic. So this is the original spectrum where you can see how my emissions are over the limits compared with this specific limit. No? If we remove the limit, we get this picture. It's exactly the same picture, but without the limits. So what happened if I measure with the spectrum analyzer, like I have done now, the differential mode? The differential mode is this one. So this is differential mode, and this is the total. Differential mode and total. You can see that this is very common from measurements, that in the total spectrum, usually the low frequencies that are coming from the switching frequency of the power supply are usually differential mode in origin. And the high frequencies have a lot of components from the common mode because of the parasitic capacitances, no? So this is differential mode, and this is the total. Or this is common mode, and this is the total. Obviously, this is differential mode, and this is common mode. To be able to compare, we need to put the same scale. So differential mode and total goes to 80 dB microvolts. So in common mode, I need to go here and change the scale to go up to 80. So we can really compare, no? So this is the total. This is the differential mode. You can see that in this frequency range, there is a lot of reduction. And if you see the common mode, the frequencies in this frequency range are important, but at the low frequencies, this is not so important that in the differential mode. So this peak, this frequency is basically differential mode. So you need to filter this frequency with some kind of parallel capacitor between the lines or a series inductor. But if you want to fix this area here, probably we need to introduce both filtering, differential and common mode, because there is no something especially dominant in one of the modes, no?
So we were talking about the scope, and now we have this third software, which is maybe something what a company which is doing maybe a lot of measurements, they would like to use this kind of software because it can be useful.
Yes. The software is able to control different instruments and to make measurements in some kind of repetitive way and creating automatic reports. So this software is typically very useful when you have a laboratory doing a lot of tests and you want to save time.
What is so it's called Electra?
Electra. It's
and
a software.
It is who created this software?
It's from Roland Schwartz.
Okay.
That is because when you select the instrument, you will see that a lot of instruments are from Roland Schwartz.
So what do we have inside of this software? What can we do with it?
Okay, inside of the software, what you can do is basically to create test templates. Test templates are, how to say, you can create typical tests that are related with a specific regulations you are interested in. For example, you can create a test template related with this EN 55014 regulation, and inside of the template, let me see, is created here. Inside of the template, you can introduce what instruments you are using, how are the correction factors, you can introduce the limit levels. This is something like when you create in Word a template for a letter or for some kind of document, no? So when you have this template created, every time you want, you can create a test. This is different. That is because you see here test template and test. So you can have different tests based in different templates.
So test is actually the measurements, what you are going to do. And template is just starting point.
Exactly. The template is some kind of the programming of the test you are interested in, the configuration, what instruments, how they are connected, how is the frequency response of the different elements, what limits you want to compare. And with this template, you can create different tests. And the tests really are the results of when you run the test is when you have the results following the template that was used to create the test, no? Obviously in the software, you have additional elements like, for example, the device list, the devices you are connected to the software, EMI receivers, spectrum analyzer. In this device list is where you choose the instrument you are going to use in the different templates. You have tables that are related with the limit lines, with the attenuation factors, with the transducer factors of the different elements. And you have another tools like for example, unit converters or the administration of your software, blah, blah, blah. So the idea basically in the software, the most important thing is the test template and the test. And because you have a lot of test templates, considering a lot of different regulations, sometimes it's very useful because you only need to go to the specific template that is related with your product, and you can start from the beginning to measure. And the result of the test is usually something like this. You can save different results. For example, I am recording here what happened with my total emissions, what is the differential mode part, the common mode part, or for example, you can introduce different measurements with different filters in your application. I have introduced a parallel capacitor, an additional inductor, or any other change you want to try in your
system. So basically, under one graph, you can see all the kind of different results which you measured during your test.
Exactly. So you can compare or you can report.
And so how do you measure it? There is some kind of start button, or?
Yes, once you have the test ready, you can click here, start.
Okay, I see.
And then automatically the software start to apply the template you created for this test, and he will be measuring in the frequency range of interest with the resolution bandwidth you want, with the limits you want, and then you will get the picture on the screen.
So no clicking or anything. You just press the play button, you will wait, and it will appear.
Exactly. That's all.
And that's everything for today's video. I would like to say thank you very much to Arturo, especially because he had to prepare this setup and some materials which you could see in the video. So thank you, Arturo. And I would like to know your opinion. Leave comments. What do you think about this video? What other kind of EMC videos you would like to see? When you leave comments, I get some feedback if what I do is good. And also, when you leave comments, it is some kind of motivation, which is telling me that what I'm doing, it makes sense and people are watching it. So, okay, don't be afraid of leaving feedback. Thank you very much. If you like this video, don't forget press like button. If you would like to see my future videos, don't forget to subscribe so you can always see when I release a new video. Usually it's every Thursday. I would like to thank you very much for watching and see you next time. Bye.